what does BRST close, what does BRST exact, what does BRST cohomology? Okay, so the words closed, exact, and cohomology have meaning beyond BRST. Okay, they've got meaning in linearity. Okay, so suppose you've got some space, some Hilbert space, let's say. Okay, you really need the inner product. But anyway, let's suppose we've got a Hilbert space. Okay, and you've got some operator, I'll call it Q so that you think of it as BRST, but a mathematician would most likely have called it. Okay, now you've got an operator such that Q squared is equal to. Okay, in many different contexts, the following problem very naturally comes. Okay, the problem is the following. First, you make these definitions. Any state psi such that Q psi is equal to 0 is called Q closed. Any state psi which is Q on chi is called Q exact. Okay, now cohomology is the following notion. Consider the set of states psi such that Q psi is equal to 0. So psi is Q closed. But psi is regarded equal to psi plus Q on C for arbitrary theta. Okay? So what have I defined in this line? I've defined an equivalence class of states. Okay? I'm not talking about states anymore, I'm talking about equivalence class of states. Any two states, firstly the equivalence class of states are all equivalence classes of closed states. Two states are said to be equivalent if their difference is Q exact. Okay? The set of all equivalence classes of states with this definition is called Q cohomology. Okay? Now, since we started talking about the general properties, let me tell you about something else that's generally true. In the case when we have an inner product. And something else that's generally true is this. There is a one-to-one map from cohomology to solutions of the equation Q dagger plus Q dagger Q on psi equals 0. Such states are sometimes called harmonic states. Okay? So this looks like a completely different problem. Okay, let me consider states such that Q dagger plus Q dagger psi is equal to 0. It looks like a completely different problem. But actually I'm going to explain to you that it's the same. Firstly,
one-to-one between this and
Q cohomology. Let me explain as I explained earlier. Okay. Firstly, I want to show you that psi is Q closed. So how do I do that? I can remember. I'm assuming we've got a positive there. Okay. So we've got Q dagger plus Q dagger Q on psi is equal to 0. So the only way this can happen is if Q on psi is equal to 0 and Q dagger on psi is equal to 0. This is clear? Okay? So in particular states that obey this equation, in particular are Q closed. In fact, they're also Q dagger closed. Okay. That was of course easy. So any state that obeys this is closed. Now what I want to show is that there is one and only one element of each cohomology class that obeys this equation. Do you understand? Okay? That in the equivalence class of states that are equivalent up to Q exact, there is exactly one state that obeys this equation. We're not going to need any of this, at least in the next lecture, but since you brought it up, it's nice to see. and the structural properties. Is the statement clear? Now I'm going to try to prove it.
So Q exact always means Q close.
Q exact is always Q close. You're right. Because if something is Q exact, then you act on it with a Q, it is automatically Q close. I mean, because Q square is 0, you get 0. Okay? So, simple examples of Q closed states are exact states. But the point is that in physical applications, these will be trivial examples. So, what we are trying to do is to count all the non-trivial examples. That's what you get from these equivalence classes. Okay? You understand why they're trivial, right? Because as we've seen, inner products of, if you put any Q exact state, you get all the same results as if you didn't have it. So they physically, that was physical reason to define this equivalence class. Okay, now I'm going to show you algebraically that this problem that in every element of Q cohomology, every Q cohomology class, there is one state that obeys that equation. Let me try to show you. Suppose I've got some state psi, okay, and I look at all elements in Q cohomology, the equivalence class. So I've got psi plus Q chi. Psi, this state which is Q, which I'm assuming is glucose, generates this cohomology class. Okay. Now I'm going to ask the following question. Which element in cohomology class, in the cohomology of class, has the smallest norm? Okay? So what I'm going to do is extremize the norm of this side over all possible elements of cohomology class. Let me assume that by luck I've chosen the psi I've started with, to be the one that has the smallest norm. Okay, there's some state in cohomology class that has the smallest norm. Let's say that state is psi. What that means is that if I vary the norm with the variation Q chi, that variation must vanish. Because it's a stationary point for the norm. Okay? So, but what's the variation of psi? Delta psi is equal to psi Q chi plus chi Q dagger psi. Sorry, I got confused. Sorry, just okay, I need more, but anyway, let me go ahead. Sorry, I go reconstruct this. Okay, so suppose this is true for arbitrary chi. Okay, now this and this are real and imaginary parts of the same matrix element. So this is some matrix element A, this is some matrix element A star. But if I've got this for chi, I can multiply it by some complex number times chi. So suppose this is some matrix element Z. This is some matrix element Z star. Okay? Since I have this for every chi, I can in particular multiply it by some complex number alpha times chi. So what we have is that alpha Z plus alpha star Z star is equal to 0 for every alpha. Okay? But that can only be true if Z is equal to 0. This is true for every alpha. If alpha were just a real number, that would tell you the real part of Z is 0. But alpha is not real. So now you choose the face. You show it. Okay. So this guy is equal to 0. So this guy individually must vanish. Okay? And that in particular implies that Q dagger on psi is equal. That is the only way this can work. Let's take this guy. This Q dagger on psi is equal to 0 because this vanishes for every guy.
Yes, we already had that from the above when we demanded that QQ dagger plus Q dagger Q on psi.
No. Now we're not stopping this. See, we're doing two ways. A, if you had a state that had this, that obeyed this, we've shown that Q on psi is equal to 0 and Q dagger on psi is equal. Now refresh. Forget about this. Now we're looking at a Q cohomology class. Because some psi not necessarily obeying this equation. Any Q closed state psi, Q on psi is 0, but no other edge.
In the negation of the norm, won't there be a term like bra chi, Q dagger, Q tape chi?
Let's do the variation. It's psi, delta psi is equal to delta psi plus psi, delta psi. This is first order variation. Is that the point? Okay. Anyway, so delta psi. So this is equal to you understand, right? Psi q psi plus psi q pi. Now put it up. Okay, this becomes dagger. Okay, clear? So what have we concluded? We've concluded that if we choose psi to be the state in Q cohomology that has the smallest norm, under just addition, okay, of course you can reduce the norm by scaling. So one second. Okay, but if you choose just let's say go to this class by psi goes to psi plus Q something, then that psi also obeys Q dagger on psi is equal to 0. But if Q is on psi is equal to 0 and Q dagger on psi is equal to 0, then clearly this equation is clear. Okay? So in every state there is a state of in every equivalence class there's a state that obeys that equation, and in fact that state is unique. Okay, yeah, please.
How do you know that in the equivalence class the extremum exists?
How do we know that the extremum exists? How do we know that the extremum exists? You see, how do we know that the extremum exists? Suppose it does not. You see, we've got a Hilbert space. We're trying to find the minimum now, because there's no maximum or something. Okay? We're trying to find the minimum. Now, in the set of all the states, there is a minimum norm, which is 0. Therefore, the extremum must exist. Okay?
What if it is a saddle point? Maybe a contour of
What does that mean? Of all the states, I choose the one with the lowest norm. It can't go below 0. Must be some state with the lowest norm.
This is only true for this closed Q closed. Means if it's a Q exact.
Psi is assumed to be Q closed as we start this proof. Okay, now you might be worrying that this may not be a mathematician's proof. Okay. You may have to worry about various subtleties, but it's at least reasonable, right? I have to say I've never faced this question. Okay. Sorry, if something is seriously worrying you, please come back.
All these states have to be physically equivalent, don't the norms have to be the same?
If all these states have to be physically equivalent, don't the norms have to be the same? Yeah. Now, we were in the space of physical states. We will define an appropriate norm to make that. This is correct. Okay? But that's not the norm we're using here. We're using a norm in the embedding space. Okay, let's Worry about the physical interpretation. You'll see how that works actually. Okay. Sorry. Any other good question? Any other questions? Yes.
So I'm analyzing all the mathematical equations. When you have that one, this is what delta cross equals 0, and that's why you pick particular forms with potential and all that. I don't see what Q dagger Q will look like in there.
Okay, so the question that Ronak is asking is actually the question that gives rise to all of this terminology. If you ask a mathematician, give me an example of cohomology. The first thing any mathematician will say is the cohomology of differential forms. Okay, so let me tell you about that. This is taken as a field, but anyway, let me tell you about that. Okay, so actually before I start, are you happy with this? Huh? Okay, so now I will explain. This, as I told you, is called a harmonic state. Why is it called harmonic? It's come from the theory of differential. Do you know on the space of functions and of forms, is there an operator that you know about that satisfies these q squared is equal to 0? Of course there is. This is extreme error. On the space of forms, it squares to 0. Okay, all of you know this.
D or D squared?
What?
D squared on the side or D on the side?
D squares to 0. So D squared is a 0 operator. D is a null operator. Okay. Now, all forms, the set of forms that are annihilated by D are called closed forms. The set of forms that are D of something are called exact forms. Okay? And the set of forms that are closed, modulo those are exact, are called forms in D cohomology. Now, what is the dagger of this field? Dagger of D is sometimes called D star. And in fancy mathematicians' language, it goes as follows. Take a function, Hodge dualize it. Take a form, Hodge dualize it. Then act on it with D. And then Hodge dualize the answer. Okay? Well, let's look at the structure. D maps K forms to K plus 1. All of you know that. So suppose I first Hodge dualize. K will be mapped to D minus K. P minus. Let's say we're P spatial. P minus K. Because that's what Hodge dualize does. Then you act with D, so you increase that. Say map it to P minus K plus 1. Then you Hodge dualize. So it maps to K minus 1. So this operation, the operation D star, okay, has the property that it maps K forms to K minus 1 forms. Okay? That's exactly the kind of operator that can be the Hermitian conjugate of D. And in fact, you can easily check that these two operators are Hermitian conjugates of each other using the inner product, obvious inner product. Right? That you've got some form with some number of indices, you define the inner product to be square root G, A mu1 to mu n, A mu1 to mu n. You raise with the metric. Contract, square integrate. It's the generalization of the L2 norm for functions. Okay? That's clear, right? So, you can check for yourself. I won't bother to do it. It's so obvious that with this definition of the inner product, this D star is the Hermitian conjugate of D. Now, what is D star plus D star D? When you act on scalar functions, do you know what you get when you work this out? Yes. Okay? So, D star plus D star D inherits the name from its action on scalar functions called the Laplacian. It's basically d mu d2 acting on forms. Okay? Anything that's annihilated by the Laplacian is called a harmonic form. And the thing that we just proved, you just repeat the proof replacing D with Q with D. What we've just proved is this famous result simple result. It's still bedrock of whatever that field in mathematics called, algebraic something or the other. Okay. It's the bedrock of a field of mathematics, which tells you that there is a one-to-one correspondence, okay, between differential forms, cohomology of differential forms, and harmonics. Okay, in mathematics, of course, there is one more thing. They link the number of these cohomologies to number of cycles. Okay, to number of non-trivial cycles in the manifold. That will really be taking us too far. I don't know, review now. This is really good. No analog for the honest teacher. So I won't try to review that. Okay, but yeah. So what we're talking. Why did I say all this? I said all this provoked by Urunago's question. Just to tell you that these are simple, basic things that you encounter in many different areas. So if you're not already familiar with the terms, you should. Okay? These are simple ideas. Of course, they take some getting used to. But getting this into your head here helps you also when you are trying to do differential. Okay. Any other questions? Why it's unique? Yes. Okay. See. Yeah, okay, it's a good question. I have proved that today. So, clearly the minimum state guy satisfies this. Now, you could ask, maybe this was Mankesh's question, could there also be solutions? Could there also be solutions here that are not the minimum number? Okay. Yes. So could there be harmonic? Could there be two harmonic forms with the same cohomology? They cannot, but why not? Let me think this one. Basically, I will have to try to make this work. But you see, it's basically the fact that Q dagger. You see, what's the point? Let's see if I can make the proof. Suppose we know that there is a state psi such that Q and Q dagger and ideal. Now, I want to ask, can there also be another state? Okay. Can there be a state psi prime which is psi plus Q chi, which is also annihilated by Q dagger? Okay. So since Q dagger annihilates this, that means that Q dagger annihilates this. So we've got Q dagger Q on chi is equal to 0. Now multiply by chi. That tells you Q chi is equal to 0. So this state was 0. I'm impressed with myself. Okay. Any other tricky mathematical questions? Okay. Clear? So are we all very happy with the general structure of cohomologies? Happy now to get back to the specific case of our cohomology? Okay, excellent. Okay, So now what we're going to do is study the particular cohomology that we have interest in, namely the cohomology of the BRST operator of string theory in much more detail. Okay, but before that, in order to set preparatory stage for that, it would be nice, it would prove useful to have an expansion of the BRST operator in terms of modes of the free scalar B and C system. And so I'm going to go and prepare something I forgot to tell you about when we were discussing the Taylor or algebra, let's say the free boson, namely about mode expansions. Okay. So let me remind you. So we're going to work out mode expansions just with the stress tensor, just to get warm-up practice. Then we'll work out the mode expansion of the BRST. Okay. How about the mode expansion of the elements? So if I remember right, we had T was equal to -1 by alpha prime del X. Okay? And we also had T is equal to sum over M Lm minus X to pi plus 2. Okay? In addition, we had X was equal to, and here I might need some help. Some square root something. Let me call it del X. Del X. Somebody help me with what? This was del X. What was our mode expansion of del X? Alpha prime by 2 minus something like that. And then of course it was sum over M. Alpha M by this X. That's what. But help me with this. If somebody can rotate when the notes are great.
Yeah. Minus I square root alpha prime by 2 summation alpha n by z.
Excellent. Okay. So now what we can try to do is to put these things all together. Okay? What we can try to do is to put these things all together. That is to find an expression for the LMs in terms of the alphas. Okay? So let us first proceed very crudely. So crudely that we ignore operator ordering ambiguities and then come back to more technical stuff. Okay? So we ignore our operator ordering ambiguities, we can just treat these like numbers, just substitute this into this. Okay? So we've done T is equal to -1 by alpha prime. -1 by alpha prime by 2 with a plus now because the I squared to -1. So that's just half times sum over M and N, alpha n z over M plus N plus 2. Right? Is that clear? Comparing with this thing here, we conclude that Ln is equal to half sum alpha m minus n alpha n up to operator ordering them. Is this clear? Pretty easy, right? Now, what about the operator ordering? Where could we potentially add operator ordering? You see, alphas with different indices, alpha 1 and alpha minus 3 just commute with 1. It's only things like alpha 1 and alpha minus 1 that don't commute. So you see, this expression is unambiguous for all m not equal to 0. 0 is the only place where things could potentially give trouble. Okay? So what we will do to play safe is we say this plus delta m0 times C times some constant. It's got a D, so you're going to mix it up with center charge. I don't yet know what D is. But this is going to be the expression for LMs. This is going to be the expression for LMs in general.
So what is the problem with M0?
M0 you have terms like alpha minus 5, alpha 5. We have to know which order to put them in. And depending on the order, you get different numbers. Because that's non-trivial computation. Okay? This is exactly the same issue we faced when defining the ground state energy of the spring. Okay? Okay, we have to know, regularize, all of that. Alright. So, one way of doing it would be exactly that way. But now I'm going to give you another more sophisticated way of fixing this one.
Sorry, what does the delta function do in that case?
It's just, see, the operator ordering ambiguity, any two alpha minus 5s and alpha 5s, the ambiguity is just up to a number, right?
Yes.
Okay? So, whatever is ambiguous is just a pure number. The ambiguity appears only in m equals 0, so that's this delta and 0, and some number d. That's what's being said. It's being said that ln has an unambiguous expression, except for n equals 0, in which case the ambiguity is at most some number. Is this clear? Okay? Now, how do I determine this number? One way to determine it is that we very carefully use these contour techniques to compute the commutation relations of the L's. So let's use these commutation relations. See, Lm's are unambiguous except for L equals 0. So if we find some commutation relation such that L0 appears on the right hand side, that will determine what the nominator function is. Okay? So, if you now use L minus 1, L1, was it m minus n? Maybe it was 1 n minus 1. Is equal to 2l0. Where Lm, Ln is equal to m minus n. L of m plus n. This was correct, right? Okay. So let's use this particular one. Okay. Now it's just simple algebra because what was L1? L1 was equal to sum alpha m plus 1 by 2. Has to add up to it. What?
1 minus 1.
Okay. Okay. And L minus 1 was equal to sum over n alpha minus n plus minus 1 by 2. Okay? And now you have to compute this commutation relation. Okay, so let's once do it sort of carefully. Okay. So how does this go? Let's take this and okay, let's take this and break this up into m greater than 0. Okay. So this is equal to basically we get each pair twice. Okay, so we get some alpha m plus 1 minus m plus 1 by 2, m is equal to 0 to infinity.
We have not put 0 of L1 to infinity comes first.
What? This one comes only once?
The 0 of 1 only comes once.
This one comes only once. Let me think about that. So we will get alpha 0, alpha 1 if we chose m equals 0 here, but we will also get it if we chose m is equal to 1. Every pair comes twice. The two different numbers could come in one. Yeah. Okay. Similarly, this guy was equal to sum m is equal to 1 to infinity, let's say. Alpha m, alpha minus m.
2 is minus 2.
Minus.
then the limits are wrong. First line the limit should be n equals 1, second should be n equals minus 1.
This should be n equals 1. Let me think about
Because 0
that.
and 1 are given the same number.
This one gives 0, 1. The next one gives what did I want? I wanted. Yeah, maybe I should write it this way. Thank you. M plus 1 minus m. Now you'll be happy. This is 1, 0, 2, minus 1, 3. Okay? And they get the limits wrong on this one. Let me see. What do I want? I'll put it at 0 and put the minus guy. So alpha minus m, alpha m minus 1. So this now work. Okay, sorry. Maybe it's easier. Sorry. Maybe it's easier to write L1 is equal to alpha 0, alpha 1, alpha 1, alpha minus 1, alpha 2, alpha. Okay. L minus 1 is equal to alpha 0, alpha minus 1, plus alpha 1, alpha minus 2, alpha 2, alpha 3. Okay, this is what it is. Okay. Now let's take the computation. Okay. Now let's take the commutators. Okay. So, what do we have? We can only get this guy and this guy give non-trivial commutator, and this guy give non-trivial commutator. But no term in this gives a commutator with any term in this. Okay, so we've got a nice and pairwise. Okay, so let's compute this guy, for instance. Okay, so alpha minus 1 with alpha 1. So alpha minus 1, alpha 2, commutator alpha 1, alpha minus 2. Okay. Yeah, well, these are painful calculations. Okay, that's good. So this is equal to alpha minus 1, alpha 2, alpha 1, alpha minus 2, plus alpha minus 1, alpha 1, alpha minus 2, alpha 2. The property of this AB formula for computation. Now what is alpha 2, alpha minus 2? That commutation relation was 2. Okay? Alpha m, alpha minus m was m. Okay? So here we get 2 alpha minus 1. Okay? And here we will get minus 1 alpha minus 2. Alpha minus 1 and alpha 1, yes, right? 1, and here we get minus 1 times alpha minus 2 alpha. Okay. Now, what about this guy? That's what happened here. What about this guy? Okay, it's clear that it just goes on, right? So here we would have had the 3's. Okay, so we would have got plus 3 alpha minus 2 alpha 2 minus 2 alpha minus 3 alpha 3 and so on. Okay, so look, this guy alpha minus 2 alpha 2 is coming with a factor of 2. Okay, so we're getting 2 alpha minus 2 alpha 2. I'll just write one more to be clear. So plus 4 alpha minus 3 alpha 3 minus 3 alpha minus 4 alpha 4. Okay, so each of them is coming with the same factor, the factor of 2. We have to be careful about what happens at the edge. This is special because alpha 0 commuted itself. Okay, so let's work out what happens at the edge. At the edge is very simple because here we just get 2 times alpha 0. 2 alpha 0 alpha 1.
Not true.
1, thank you. 1 alpha 0. Right, yes. 1 alpha 0 alpha 0. Okay, so where are we? So we're going to alpha 0 alpha 0. Plus 2 alpha minus 1 alpha 1 plus 2 alpha minus 2 alpha 2 and so on. This is exactly the formula for L0 because L0 is exactly the formula for 2L0 because L0 was half sum over m alpha minus m and was normal ordered. Normal ordered everything because T itself was normal ordered. Expression. Okay, so we get exactly 2 times L0 with no normal order constant. Because you see, work this out carefully, and every time the positive guy has appeared to the right of the negative guy. So it automatically turned out to be normal order. And so that one constant that we call D was just equal to 0. Okay? Now the fact that we got this normal ordering constant 0 was true of the free scalar field. Of course we know it's true. We know that the identity operator has L0 equals 0. Or the state corresponding to the identity operator, the L0 equals 0. You know, we knew that. So we knew the answer beforehand, but I'm just telling you how algebra could have been used to get it. Okay? Now, in an entirely analogous way, we can work out the mode expansion for the PRST charge. Okay? So let me do that. Okay, so first let's remember what the BRST constant is. So QBRST was equal to C times D plus somebody help. What was the next term?
C times B cost.
Half C times B cost times C times del C.
Yeah, that is equals to BC del C.
Half D G D cost. Plus what was the other term? Some del square C.
Right to del C.
Del square C. Good. Okay. And okay, fine. Which was equal to C matter plus, and give me the other form as well, please. C del C B. B C del C. Plus 3 by 2 L squared. Okay, excellent. Okay. Now it's just a matter of, okay, let's at least approximately see it. Okay, so what's T matter? T matter was, just wrote it down, Ln by z to the power n plus 2. Now by L I mean L of matter. Don't write matter. And what was C? C was sum over m, Cm by z to the power m plus what? Minus 1. Because C has 8 minus 1. And B was equal to sum over m, Bm divided by z to the power m plus 2. Okay, superb. All we have to do is to plug this in. So let's first do it naively, and then we'll do it more carefully. Right on normal orders. Okay. So the easiest, of course, is here. Okay. So if we just plug this in, what do we get? Here we get 3 by 2, and we get del square. So 2 dels acting on this. So minus m plus 1 into minus m into cm by z to the power m plus 1. Which one? Okay, so this term is just equal to m into m minus 1, 3 by 2, cm by z to the power. Okay, so that was the first term. The second easiest term is this guy. That is equal to sum over c, let's call it LMC minus, okay, I want totally this was not QB, this was J. Yeah. So JD is a current. So I'll expand it like z to the power n plus 1. So I got that n plus 1 up there. So I'll continue to have n plus 1. So that's perfect. C m sorry. So I want this guy plus this guy to be m. M minus k c k over z to the power. Let's check. Right, because this would come with a factor of z to the power m minus k plus 2. This would come with a factor of z to the power k minus 1. Adds up to z to the power n. Okay, so this guy is the second term in the expansion. Okay, now we have to be even better. Okay, so what about the third guy? This guy. Here we need. Okay, now if we just use BCC, we would get z to the power n, because B comes with z to the power n plus 2, and C's come with z to the power n minus 1 with the 2 C's. But we use a del on C, right? That's what gives us the z to the power n plus 1. Okay, so we'll keep track of what this guy was. So let's call this guy the special guy. So let's call it CK1. This guy is also special, CK2, and this guy is BM minus K1 and minus K2. Because we had a del on this guy, we will get a factor of minus K1 minus 1. Please check. Do you agree that K1 and K2 are something special? Do you agree? The expansion of that term is the same. Okay? Now, ignoring normal ordinary constants, we just have to collect terms. Okay? So if we were to ignore normal ordinary constants, okay? If we were to ignore normal ordinary constants, we would conclude that Qm, but I'm not interested in Q, let me just get QC. So, the term in the expansion here at m equals 0 is the BRST term. Right? So, QBRST is equal to what? This term just gives 0. This term gives L minus K C K sum over K. I think it would be more conventional to write it as L K C. Okay, sum K equals minus infinity. Okay, and what about this term? We have M equal to 0, so we get B minus K1 minus K2, CK2, CK1 plus minus K1 minus 1.
For 1 over sake.
No, the BRST charge is the coefficient of 1 over 6. Okay? First, let me check the rest. Is my thing right? Okay, so there's C times L, so that of course is right. And they write it as M minus N by 2, Cm, Cm, D minus N minus. That's wrong. And Pulchinski wants to make it symmetric between the two Ks. Okay. So he claims this is equal to check L K C minus K. See, he writes it as plus M minus N by 2 Cm, Cn, D minus. Okay, let's see if these two are the same. Yeah. You see, this one part just gives you 0. Okay? Because this is anti-symmetric in K1, K2, but the pure summation is symmetric. Okay, so that just goes away. For the same reason, this K1 can be replaced by K1 minus K2 by 2. Only the anti-symmetric part contributes. Okay? So that's K1 minus K2 by 2, and now is the overall sign correct? So we get, the guy that's second comes with a minus sign, which is what is here. Perfect. Okay? Up to normal ordering constants, this is the expression for the BRST charge. Are you happy? Okay? Now the issues of normal ordering constants. What term here could have had normal ordering? Could have given, has an operator ambiguity, ordering ambiguity. Which term? CM, no ordering. C with B. Okay? Now, suppose you had the only ordering ambiguity is with C with B with equal and opposite indices. Okay? But if these indices are equal and opposite, that fixes this index to be 0. Okay? So the only possible normal ordering ambiguity is plus some number hash times C0. If we've not done the ordering carefully, we could have made a mistake in such a term. It's the only term we could have made a mistake. Okay? And now we're going to fix this term. We're going to need some commutation. I'm going to follow the same methods. So we're going to need a commutation relation to fix this term. What commutation relation do we use? It proves useful to use the one we worked out at the end of the last class. At the end of the last class, we showed that Q with B0 was equal to L0. Was equal to L0 matter plus cost. Do you remember? Anti-commutator. Both are. Okay? So, I'm going to use this guy because both of these I know unambiguously. Okay. I haven't worked out what L0 host was for you. Sorry. I haven't worked out what L0 host was for you, and I'm going to leave that here. Shall I work that out? Leave it as an exercise. I should have worked out the host thing, right? Yeah. Okay. See, sorry. What have I not done? What I should have done if I was being systematic in this class is after working out the normal logic constant for the matter LMs expressed in terms of oscillators, I should have done the same for the cost. Okay, these are the two things we need. I didn't do that exercise for you. Would it be okay if I left that as an exercise for you to fill in? Okay, the only thing that makes me hesitant about that is that you get non-zero non-term constant. You might want to see how that works. Okay, let me spend 5 minutes to work. Okay, sorry, we'll just do it. Okay, let's just do it. Okay, so you treat this as a result that we've got up to normal ordering constant. We're doing a slight diversion calculation now, and we come back to fix that up. So, where are we? I need to know what the expansion for the coast for the coast L0 was, the coast LMs were, in terms of mode expansion for the coasts. So let's do that. If someone can help me with the formula, that was it. Minus 2 del BC plus del BC. Del BC minus 2 del BC. Excellent. Okay, so now we'll very quickly work out this guy. Okay. So T will be equal to, so Lm, let's just write on it. Lm will be equal to Bk minus of k minus 2. Sorry. Minus of k plus 2 minus bk c m minus k. Okay. Now what about this guy? Minus 2 into minus m minus of m minus 1.
Was easily written like minus del BC minus twice T del C. So that would have been.
Okay. Since I started with this, if you don't mind, they're all equal. So minus 2 minus m minus 2. Okay, sorry, what was you want to say minus of this plus? Okay, that's it. So Mangesh wants me to put a plus here. Minus has changed. Plus. And he wants me to write minus 2 b del c, right? Okay. So now what's this? This is minus 2 into b of m minus k ck, and then this guy got differentiated, so it gave you a plus 2 into k minus 1. What do you agree?
We swap K and N minus K.
I swap k and n minus k, it will be better. No doubt. But first, if you don't mind, tell me you agree with this. I did this so that I got this guy inside. So whatever this is 2k plus. Yes. Okay. So now Mangesh wants me to swap. So I'll swap. LF is equal to k plus 2 bk minus k plus 2 into. Okay. So that is equal to 2 plus 2m minus 2 minus k minus 1 minus 2. Okay. So 2m minus k bk c m minus 2. Okay, so 2m minus 2 bk, I'll just check this against. Okay. bk good. Minus k. Perfect. 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 Okay, so this is perfect. Ignoring normal ordering constants, this is the answer. Okay, what about normal ordering constants? Which term here could have normal ordering constant? L? L0. Okay, m equals 0. It would have to be just a pure constant. So some number times delta times 0. This is the most general form of the stress tensor in terms of mode expansions. Okay, and now okay. Now once again we're going to determine this normal ordering constant by looking at the L minus 1 element commutator. So suppose you look at L minus 1, L1 is equal to L0. So now what was it? So L minus 1, which was unambiguous. Okay, fine. Yeah. So here, because we've got separation between B's and C's, it's very easy. Yeah? So we've got L minus 1 is equal to minus 2 minus k into, sorry, L1. Okay, L minus 1 is minus 1 minus k, B minus k, C minus M minus k. Sum L1 is equal to 2 minus k prime, C minus C. Thank you. B minus k, C 1 minus k. Right. B, K. Thank you. And here K prime. Okay. Now we want a non-trivial, we want the commutator, anti-commutator. The commutator between L1 and L minus 1.
Can I ask you a small question? Like when you are fixing up the ambiguity, like delta L0, when you are considering L minus 1 or L1, those terms are not appearing at all. So how an L1 and L minus 1 commutator always gives you L2 L0.
Yes.
But how do you determine that part?
That's the point. Because L1 and L minus 1 are unambiguous.
Okay.
Their commutator is unambiguous and therefore determines that.
But that is always 0 in L1 and L minus 1.
No, you see, the question is what it turns out to be once you take the commutator. It's not like L1 and L minus 1 are constant terms, but they're commutative.
You're basically comparing two different ways of calculating LC.
Exactly. Is this clear? Great. So now all we have to do is to compute this commutative. Okay. So now what we want to do is to compute sum over k prime 2 minus k prime into minus 2 minus k commutative b k prime c 1 minus k prime b k c minus 1 minus k prime and k. Okay. So now we use the same formula works, right? The same formula works. So this is equal to 2 minus, I'm not writing the summation, 2 minus k into minus 2, so let's write it, minus 2 plus k. That's why this is plus k prime minus 2, k prime plus 2 into k prime minus 2. Okay, into what? Into one term is b k prime times commutator of c1 minus.
You have to be careful. Right now, we need to convert the commutators into anti-commutators.
But so far, at the first step, it's just commutators because this is with a bilinear. Okay, bk c minus 1 minus k plus bk prime bk c minus 1 minus k into c 1 minus k prime. It's a painful calculation, sorry. Okay, now we have to do what Mangesh was warning us. Okay, we have to compute. Yeah, we have to turn those into anti-commutators. Okay, and Mangesh is warning us that we might mess up. I think that we get the right answer if we just keep track of the signs. So I'll write down a formula and you tell me if you do. So this is k prime minus 2 into k plus 2 into b minus k prime into first term here with a minus sign. Minus bk into c minus, okay, now c minus 1 minus k prime, c1 minus k prime, okay, only works, oh, that's 0. See what c is 0. Okay, yeah, okay, so this is pretty easy. So let me do this again. So that's bk prime, it's just this anticoat. So that only works if k is equal to k prime minus 1. Right? Delta k prime minus 1. And what's left is c minus 1 minus k, and have we got the sign right? I think we will close that. I think we will close that. Okay. So that's the first term. I'll just write down the second term and then we'll process. Yeah, let me write the next term, then we process it. The point is that there are going to be some terms here that will appear out of normal order. And so we will get a normal order. That's the main point I want to make. That's why I did it as an exercise. But since we're doing it, we have to do it. Okay. Here, what do we get? Here, the only non-trivial combinator is this guy with this guy. So, that's the term when we take this guy out here. That should give us a minus sign, right? Okay. So, that should give us a minus bk. Then bk prime with c minus 1 minus k. It only works when k plus 1 is minus k prime. K plus 1 is k prime. And k plus 1 prime. C minus C1 minus k prime. Okay, has anyone found a mistake in this? It would be very nice if you find mistakes because we're going to make a conclusion that will go wrong. Everyone agree with this? Excellent. Okay, so now we simplify. This one was delta k prime minus 1. Okay? So let's write it in terms of whatever we had at B. So delta k is k prime minus 1. So k prime minus 2 into k prime plus 1. B k prime and k is k prime minus 1. So that's C minus k prime. Okay? What about this term here? This term was, once again we keep the guy, this B guy, I'll write it as K and then change it to K prime. So K prime is K plus 1. So we get K minus 1 K plus 2 into minus bk minus bk in a C. K prime is k plus 1 C minus k. Now,
First line here the B minus K or B K prime? First line.
Sorry?
B minus K prime or B K?
Yeah.
So is it B K prime or B minus K prime?
Oh God. It was a BK prime?
Yeah.
Well, it was, I'm believing you, right? Yeah, one of these has to be plus. Yeah, so. Okay, excellent. Okay, so now let's just group together. So we put this K prime, K prime, K prime, K prime. Done. Okay? And where are we? Yeah, this was K prime plus, we don't get quite 0. Because this is k prime plus 2, this is k prime minus 1. Here we have k prime minus 2, k prime plus 1. The term that was constant, which is minus 2, is the same here. The term that is k prime squared is the same here. So it's only the term that's linear k prime that survives. Okay? Here we get a term linear k prime which is minus k prime. Here we get a plus k prime, but this comes with minus sign. So you get a 2k prime minus 2k prime, bk prime, ck prime, and c minus k. Okay, now what's strange here? Where have I just got calculation? Strange here looks like there's a huge number of constant. Sorry. Mess this up. First. What's strange here, since our sum was from minus infinity to infinity, it looks as if we have negative guys out there, which is very, very far from home. Why did I, how did I miss this? Just right. I got some mess up here. Sorry. Firstly, does this give you the correct 9 relationship? Especially, it's not even giving the right. No, it's giving the right 9 relationship. Up to normal order, it's giving the right answer. Because look at M, which is the guy on 0 minus. Yeah, so it's giving the right 9 thing that I've got the normal ordering wrong. Okay. Just plus. What is it? what's basically my point is. Let's try to figure that out. We had L1, which was forgetting about all details. Ek C minus K. L minus 1 was B minus B K C minus K minus. So this is plus 1, this is minus 1. Now we did the commutator of this with this. We contracted away this guy. And we're left with the C's arbitrarily. Yeah, what's wrong? We're left with C's which are very negative on the right hand side. Because the question was, what did we? You see what you see what we did wrong. See what we did wrong. The thing was that the original expressions were normal on that. The expressions for L1 and L minus 1 were normal. We didn't take care of that. So these expressions I should have written with.
C minus is this.
It should never, of course, have happened, right? Because you start with something normal order, it's not going to be such crazy. You see what I did wrong? I'm sorry. See, I wrote this as this, but I had to break it up into two cases. Do you see? I should have broken it up into whether B was positive or negative. Okay? The guy when we had one positive and one negative, you always write the positive on the right because the expression was normal with the right minus sign. That I didn't do and I'm big nice. That's basically what I did. It's very tempting to say please go. Shall I try to fix this? Will you guys work it out? Okay. I'm sorry about this. I'm sorry about this. Okay. What you need to do is break this up into two cases. Okay. I'm sorry. I should just let you fix it. Right? Yourselves were wasting 15 minutes on it. Okay. But there was some payoff. We saw what mistake one could make. Okay. So how should you write this expression? You should separate terms. Here you're going to, because this is L minus 1, you'll have one term with both negative, with minus 1 and 0. Okay? But all the others will have one negative and one positive. Always the positive guy should go on the right. Okay? Always the negative guy should go on the left. First you pay up sign price for taking it. Okay? So break it up into two terms. Similarly with L1. Okay? Redo this calculation. You get the same thing up to ordering issues.
What was wrong with this?
What was wrong with this was they started with the wrong first thing. Why didn't I like it?
Yeah.
I didn't like it because the nominal ordering constants are there at infinity. Okay, because there are, and half of these, the guy which is positive is to the right, while the guy that is negative is to the left. Sorry, in half of these. Okay, with those for K negative. But the other half, the guy which is negative is to the right, and the guy which is positive. So once I normal order, I get an infinite number. Should not have happened.
And if you have added to
Yeah. The problem was that I started with the wrong expression. I didn't start with the normal order expression. I started with just the expression itself. For the bosons, we were very careful to start with the normal order expression. I fooled myself into thinking because B and C were different, you don't have to worry. But of course, you do have to worry because B and C is different. That was the thing that I momentarily slipped on. Right? It's BC that I am on today, not CC. Okay. So this expression here, so let me just write down the right expression. The right expression should have been, well, the guy that is negative goes to the left. Okay, so split this up into, it's equal to minus 2 minus k into, when k is negative, okay, some k is negative, okay, bk c minus 1 minus k, okay, minus some k positive. Okay, when k is positive, this guy is positive, but this guy is negative. Okay. Minus some k positive, c minus 1 minus k, bk. And what about the special case would be k0? That would be b0, c minus 1. So once again, we will put c minus 1 on the other side. Okay, so b k is 0 over. Okay, this was the correct expression for L minus 1. Similarly, we tried out the correct expression for L. Okay, with the same principle. Everything should be normal. Okay, then redo this calculation. Clearly, because these things only differ by operator ordering, you get the same expression up to operator ordering. But you will get various operator ordering. Yes, and when you do that, I'm sorry, I'm just writing it down. It's taking. You will get that this L0 is equal to what we had here, the normal order of what we had here. B, K, C minus K minus the plus the C minus K with a 2K plus 2 into 1 minus 2 by 2, so it's minus 1. Okay, please check this. Please do this as an exercise to check it. I'm sorry I messed up but wasted time, and so we can check it in class, but please check this yourselves.
How is the sum over k running here?
It's runs over all.
No, but then again we'll have that same problem of...
No, now this is normal. In this normal order expression, we arrange. That's what I mean. It comes in the right order, to be normal order, plus the minus. That's clear. Okay. How did we know that this had to be the right answer? Exactly. So, Ronald points out that we knew this had to be the right answer because these guys annihilate the vacuum. Because they don't. But what was the. Yeah, but the vacuum was not identity. It was C. Okay? What was the dimension of C? Minus 1. Okay? So, we know actually, on general grounds, this has to be the right answer. Normal order constant had to be a minus 1. However, it is a worthy exercise to check it from this point. Okay? I'm sorry I messed up on it. I'll leave it to you to make amends for my mess up. Okay? But we knew that this had to be there. Right? Just because we knew that the dimension of the state corresponding, of the operator corresponding to the identity state was minus 1. This is exactly the same way we knew that the answer of the free boson theory has to be 0. Because we knew that the dimension of the state corresponding, the operator corresponding to the vacuum state was 0. Yeah, it was fine. Okay. Sorry. So let's just move. This would be too painful to do. I won't. Okay. So now let's move on and let's see if we can proceed with the BRST charge. So somebody please read out the BRST charge again. Q was what, please, up to normal orbit? Oh, into the normal orbit. CM L minus N, right? One term. What was what? M minus N by 2. CM C N B minus M minus N. And then there was a plus, some number we didn't know, times C0. Okay. Now we're going to use the same principle. The principle is that Q BRST times anti-commutator with B0 equal to Lm plus L is equal to L0 matter plus L0 cost. Okay. Now, this here, the question is whether I dare to do this. It's easier, right? Because the young guy is just B0. So it's easier, it's harder to mess up. On the other hand, here we will also have to take care of the normal orderings. Okay, give me a vote. Shall I try to work this out? Or would you like to do it yourselves? No, I see one very strong no. Anyone would be very happy if I work this out. Given our track record, it will take me at least 10 minutes. What has to be done is very clear, right? This guy is normal ordered. This mn sum here, so you have to be very careful about expressing it always in the right normal order. And then once you do that, you take the commutator. Okay? When you take the commutator, you see what will you get? From here, you get T matter plus T ghost. L0 matter plus L0 ghost. Now we know what L0 ghost is. We know what L0 matter is. So we know what we should get. Okay? Clearly, B0 with C0 contributes a constant. Okay? So if everything is working out up to the constant, then by fixing this number, then that number will fix it. You can choose that number to fix it so you get the constant, right? The constant is this minus 1. So we have to fix things to get that constant, right? Okay? The claim is that that the constant is in fact minus 1. This is equal to. That's basically the same constant. Claim is that if you just did this whole calculation like this, you would get this part of T ghost and all of T matter. This part of L0 ghost, all of L0 matter, but not the normal order constant. And so you will have to explicitly add the minus 1 to get the normal order constant. Okay? I'll let you try. If anyone has trouble doing this algebra, we can do it in class or outside. Just if you there's nothing to it. You just have to peacefully do the algebra. Okay, excellent. So let us say that let us declare this as the answer. Oh, Pulchinski's not made a typographical error. And move on. Okay, yeah, we've spent enough time on coding algebra. Okay, so now we have the mode expansion for this BRST charge. Okay, we're going to use it, but also hopefully you also now have got the hang of making mode expansions of anything you're interested in. We've seen the basic principles and how to do it. Okay, now what we want to do is to work out the BRST cohomology. Okay, so you remember we saw that in D equals 26, the BRST charge squared to 0. So the problem of BRST cohomology is very high. And what I want to do is to try to understand how the BRST cohomology goes. Okay. So, what's the full Hilbert space? The full Hilbert space is generated by B oscillators, by C oscillators, by the 26 bosonic oscillators, and by the 0 sect, bosonic 0 sect. That's the full Hilbert space on which this BRST charge acts. Okay? That's the full Hilbert space on which the BRST charge acts. Okay? And now what we're going to do, first at level 0 and level 1, and then in complete generality, we're going to try to understand the BRST cohomology. So, let us first, so B up here, so this we will write as -1 and this. Okay, so let's take states and grade them level by level. Okay, and though I'll have to wait till the end of this discussion, we are also going to impose that B0 on physical states. So, the first thing that we want is that states are Q closed. So, Q on psi is equal to 0. We have B0 on psi is equal to 0. But using this anti-commutator, it follows that L0m plus L0g on psi is equal to 0. Right now, just one. You see, it's in analogy with the point particle. We're going to get twice the cohomology that you should get. One of which will just give you 0 in all income products. The one that won't is been out. At the moment, we just said. Okay. So our states are going to be annihilated. Our states are going to be annihilated by L0 matter plus L0 ghost. Now, what's the role of this equation?
This is like saying that all states are primaries of dimension 0.
All states are primaries of dimension 0. That's exactly right. That's exactly right. So, all physical states are in fact primaries of dimension 0. That will be exactly right. In fact, we make that statement very precise by the end of the step. You'll see exactly what's happening. Okay, at the moment, it's not quite saying it's primaries. Because we're just saying this about L0. Just saying that the dimension is that. But we're going to say what Ronald said, that we are about. Okay, now what is the role of this state? This equation. This equation is just a Marshall equation. Because L0 matter includes the p squared by, the p squared by Newton. Okay? So this equation will be satisfied just by telling you that if you know the oscillator number, if you know what the oscillator number is, that will determine the p squared. Okay? Where do you see the tachyon from this equation? The tachyon comes from the -1. The fact that L0 host have the -1 in here will tell you that if you look at the state that is just a vacuum, p squared will be tachyon. This will be exactly the same analysis we did in cruder ways of looking at the bosonic string. Okay? So this equation will just give you the Marshall condition. Is not helping you in deciding which oscillators are in Q cohomology. Fine. So now, the first thing that we do is the following. What?
What is the second condition?
This B0 on psi is equal to 0. Of the two states, if you have the whole Hilbert space, it's generated by B oscillators, C oscillators, as well as a two-state system from B0, C0, 0. This picks out one of those two states. Why did we fix this? We fixed this in analogy with the point particle, and I promised you that I will come back and show you exactly why. The point is that we get in just cohomology we get twice the copy of what I'm telling you about. But those states which are annihilated by C0 will turn out as trivial scattering matrices with all other states. I will have to show you. I will have to show you how this comes about. At the moment, you just accept this. We go to the end and then we see it. Okay. So, now the first thing I'm going to do is take the vacuum state. And I'm going to ask, is the vacuum state is the vacuum state annihilated by the BRST operator. Okay. But is the vacuum state annihilated by the BRST operator? And the answer to that question, of course, is yes. And one way of seeing it is the following. One way of seeing it is just from the mode expansion. Okay? Let's see. Firstly, let's look at this step. Okay. Either we have L minus M annihilates the matter, L minus M annihilates vacuum state. Okay, otherwise it replaces the energy. Now, C minus M and C0, L0 also annihilates the vacuum state. But C minus M annihilates the vacuum states for all positive. So in this expression, one term always annihilates the vacuum state. Because either you've got the coefficient, the index on M here is either 0 or negative. In which case C was positive, C didn't annihilate it, but this guy does. Or this guy is negative. Okay? So that object always annihilates the vacuum state. Okay. Now, let's look at this guy. Okay. Let's look at this guy. This was M minus N by 2 Cm Cnb minus M. Okay, let's look at this guy in the back. Now, anything with any of these negative I said something wrong. Sorry. Let me come back to it. This guy obviously annihilates the vacuum state. Because anything with any of these is negative will annihilate the vacuum state. The only possibility is all of them 0. Firstly, B is to the right. Secondly, even all of them are 0, this is 0. So for multiple reasons, this guy annihilates the vacuum state. Okay? So this guy on vacuum state is 0. Then I told you wait a minute, down here. Just. Just one. Sorry. Okay. You see, I should only be. I'm asking the wrong question. When I ask about the vacuum state, I must look at the vacuum state put on shell. Remember we had the condition that L0 matter plus L0 ghost, okay, on psi is equal to 0. So I'm not even allowed, because I'm looking at things that are annihilated by B0 and by QBRST. I'm not allowed to look at the vacuum state with no zero mode excitation. Okay? I have to look at the zero mode excitation that fixes this condition. Okay? So I look at the oscillator vacuum state. That's what I should have said. Okay? If I look at the oscillator vacuum state, then L0 ghost on the oscillator vacuum state is -1. And therefore, L0 matter, okay? L0 matter on the oscillator vacuum state has to be equal to +1. Because this condition has to be met. Where does that come from? It comes purely from the zero mode part. Which is basically the statement that Tachyon obeys the equation. P squared is equal to something, which is not 0. Is this clear? Was that clear?
No.
Okay. Let's look at what L0 is. L0 is P squared by some alpha prime 4 or something like that. From the zero mode part, plus oscillator stuff. L0 oscillator. Okay, this is from the matter. From the ghost part, we just get ghost oscillator stuff plus normal ordering constant. Let's look at the ghost vacuum. Okay, the ghost vacuum has ghost oscillator stuff 0, but it has normal ordering constant -1. So L0 ghost acting on this thing is equal to -1. Now I want to know whether the tachyon is a BRST invariant state. Okay? So what I want to know is if I take any of the states that is in the harmonic oscillator vacuum for the matter part, but whose P squared is fixed by this equation, so as to make this up. Okay? I want to know whether I get 0. What do we know about such a state? A, that it's in the harmonic oscillator vacuum for the matter part, but B, that L0 matter on it is +1. So that L0 matter plus L0 ghost gives you -1. That's the question I'm interested in asking. Okay, I'm interested in asking whether the tachyon is BRST invariant. Okay? The tachyon cannot be said to have zero mode part equals 0 because that's off shell. As we see from this equation. Is this clear?
You don't take the on-shell condition for the matter part separately and this ghost part separately.
There's no such on-shell condition is this equation.
Also, there is a unique vacuum. Though the two CFTs are like DC CFT and the cosonic CFTs are decoupled, the vacuum is unique.
They decouple, but I'm not really interested in the vacuum. See, that's the point. I'm interested in Q cohomology. We've shown that states that are in Q cohomology and are also annihilated by B0 obey this equation. Okay? So the vacuum has L0 matter plus L0 ghost equals -1. It does not obey this equation. Okay? So the question about whether the vacuum is in Q cohomology was a stupid question. My stupidity. The vacuum is obviously not in Q cohomology because it's not Q closed. Okay? We should only be asking questions about, so vacuum is not Q closed. But that's not the physically relevant question. The physically relevant question is, if you're in the vacuum for the oscillator sector, and L0 is being made up by the zero modes, what does that do? That puts the particle on shell. Gives you the tachyonic equation of motion on shell. Is that in Q cohomology? That's the question. Is this clear? Okay? Now the answer to that is, First I'm going to check that Q annihilates the state. Okay? How do I check that Q annihilates the state? That's actually very easy. Because we had C0 times L0 matter minus C0. These were the only two things that happened. This came from the normal ordering constant, and this came from the L0 matter. But L0 matter was 1. So So this on back, I say vacuum, that's a misuse of terminology. Vacuum state. Oscillator vacuum was equal to 0. Is this clear? Okay?
But the ghost part has a minus. And this, what is that? What is the of the ghost part? L0G.
L0G is minus 1. But L0G doesn't appear. This is QPRST. We're checking to see whether this on that guy is equal to 0. So you get L0 matter minus C0. Because this had its origin in L0 ghost. So it's probably a way of writing it from the L0 ghost. But in this expression it just appears and you get 0. Is this clear? Okay? Now, what can you say about the energy of QPRST? You see, QPRST here, QPRST here never raises or lowers the oscillator. Okay? It has no terms that will, so it preserves the oscillator number. Net oscillator number, okay? The net oscillator number means oscillator number in both the matter as well as the ghost part. Because clearly you can add some oscillator number here and subtract some here. Okay, but it preserves net oscillator number. Okay? So, this state of oscillator number 0 was annihilated by Q. Now, because it was the unique Q closed state at oscillator number 0, okay, that also tells us that it's not exact. You see, because if it was exact, it would have been equal to Q on some oscillator number 0 state, but Q annihilates oscillator number 0 state. Okay.
From this, when the tachyon, this on-shell condition you have found the vector.
Yes.
From that.
Yes. Say the whole thing. Okay. See, firstly, we are only going to restrict our attention to states that obey this equation. Okay? We're going to restrict our whole discussion to states that obey this equation. Because that is a necessary condition. That is a necessary condition as we have shown. Okay? So, all our states obey this equation. L0 matter plus L0 ghost is equal to 0. On states is equal to 0. Okay? Now, you can ask, is the problem of BRST cohomology restricted to this sector consistent? That is the question of whether QBRST commutes with L0 matter and L0 ghost.
Separately or this like
Plus.
Because somehow it's just confused like the two CFTs are different. It's a two.
No, the CFTs may be decoupled, but QBRST is not. QBRST has mixed terms between C and L. Okay? So the question is, the first question you can ask is, can you consistently truncate the cohomology question to the subspace of states that obey L0 matter plus L0 ghost on state is equal to 0? Okay? Provided L0 matter plus L0 ghost commutes with QBRST, this is a consistent truncation. By which I mean what? See, the worry might have been that even if you are interested in looking at, suppose you get a state which is Q closed, obeying L0 matter plus L0 ghost, state equals 0. The worry might have been that maybe it's Q exact because it is QBRST acting on a state that did not obey L0 matter plus L0 ghost is equal to 0. Okay? But that cannot be because QBRST commutes with L0 matter plus L0 ghost. Okay? So, Urna was looking like, what the hell is this?
Let me say it.
Okay, I'm sorry.
Is it not like saying that the first and the third condition are being imposed, the fact that psi is Q closed and the third condition is true. It's the same statement as Q and L or L.
It's not the same, that's a consistent truncation of the cohomology. Okay, let me first make an argument. Suppose I'm interested in Q cohomology. Okay? And I've got some operator A that commutes with Q. Okay? Then it's consistent. Okay? Consistent to ask the following question. What is Q cohomology on the subset of states for which A on psi is equal? This is a second question you can ask, but it's a consistent question. This is not obvious because you see the restriction of Q to the subsector with up to the kernel of A need not have been an operator that squared to 0 if you just brutally truncated it.
Not just 0, right? It could be any number.
What?
It could be any number.
It could be any number, but I'm interested at the moment
Okay.
in 0. Yes, could be any number. Okay? Yeah, and you can change that just by changing A minus number. Okay? But this is a consistent problem. Why? Because you see, the first thing we're interested in is states. You see, we're interested in states that are of the form. We're interested because of this commutation relation, everything is consistent. Why? You see, we're interested in states that obey Q on psi is equal to 0. Okay? Now, suppose Q on psi is equal to 0, and you want to know whether and it obeys this equation, A on psi is equal to 0. The question of cohomology now becomes a question of exactness. I want to know, is this state, okay, I've got some state, is it Q exact? Okay, so is it Q on chi? So I've got some state like this, is psi equals Q on chi? That's the question of cohomology. Okay, now, in general, if you try to restrict to some operator, to the zero, the kernel of some operator A, you could have had a state that was exact without belonging to the kernel of A. But when the two commute, that's impossible. Because suppose Q, we know that A psi is equal to 0. Suppose psi is also Q of chi. So that means A on Q of chi is equal to 0. But this commutes. Okay? And therefore this is Q on A chi. Wait, am I getting this wrong? Sorry, let me say this. Okay. Okay. See, what do we know? We know psi is such that A psi is equal to 0. Now, suppose suppose psi is equal to Q on chi.
So that A on chi is not equal to 0, and we want to show that actually it's not possible.
Yeah, so that. Yeah, so suppose A on chi was not equal to 0. Okay, then A on psi would be equal to Q on A of chi. Now, suppose this was not equal to 0, this would be Q Okay, actually, this A is not, this A is not just any operator, it's a Hermitian operator. Okay, so let's take the whole Hilbert space and break it up in the eigenspaces of A. Okay, all I'm saying is that Q preserves the zero eigenspace. Okay, so suppose you've got Q acting on some object which has some non-zero eigenvalue, it will remain non-zero eigenvalue. Because Q commutes. So it's clear here that you cannot, that's consistent to look at the cohomology of Q in the zero eigenvalue sector of A. Let me say it again. Okay. See, all of Hilbert space can be split up. Hilbert space is equal to sum over M Hm. Where Hm, states in Hm, if psi belongs to Hm, A on psi M is equal to M psi M. Em psi M. Okay, the various possible energies for this thing. Okay. Okay. So now, suppose we look at some state which was not in psi 0. You look at Q on it. It is also not in psi 0. Okay, so an exact state which is of the form Q on something that's not in that doesn't have zero energy cannot turn out to be a psi with zero energy. I'm saying something totally obvious, but it should be clear. Is this clear? I've got this up. You've got decomposition of Hilbert space into eigenvalues of this operator. Q commutes with this operator, so it doesn't change the eigenvalues. So the cohomology acts eigenvalue by eigenvalue. Okay, so in particular, the restriction of cohomology to eigenvalue 0 is a consistent thing. Okay? Okay. So because we are only interested in states that obey L0 plus L0 goes to equal 0, we will completely restrict our cohomology question to that sector. Okay? And this is a consistent thing. It's not that something from outside that sector can come and mark us. Okay. Now let's go back to the vacuum. I'm sorry I've done this so badly. Let's go back to the vacuum. The oscillator vacuum. Okay. Let's go back to the oscillator. Okay. So the oscillator vacuum, we agreed, was annihilated by QBRST. Okay? Moreover, we agreed that QBRST didn't change total oscillator number.
And also P, right?
What?
Can I change P? I lost track of that.
Can I change P? P. No, it's actually this is 0 more even in P. It's got no momentum.
Okay.
Yeah, so I also cannot change P. Yes. Okay, cannot change P, cannot change total oscillator number. Okay, so if you act with QBRST, so now in our restricted space, the space that obeys L0 plus L0 goes to equal to 0, what are all the states of zero oscillator number? Well, it's that oscillator vacuum of the ghost times oscillator vacuum of the matter times some momentum that makes up mass shell connection. But all of these states were annihilated by Q. So the space of Q exact states at oscillator number 0 was just empty. So every Q closed state at oscillator number 0 was also Q cohomology. Okay? And And therefore, by this tortuous route, we have found that the tachyon is in Q coordinate. I'm sorry I've done this so badly. Is this clear? Okay? Good. Now let's go to level 1. Okay? I'm going to separate the left movers and the right movers just because they basically don't know. Okay? So let's list all level 1 states. What do we have? We've got some alpha times b minus 1 plus some beta times c minus 1 plus some gamma mu times alpha minus 1 mu. That becomes 0. All level 1 states where 0 was the full vacuum, the oscillator vacuum. And then the zero mode part will fix itself up to make the partial condition. I want you to talk about that. Because we're restricted to that subspace. Okay? So I'm ignoring 0 modes in it. Because that's just taken care of by that restriction. Okay. Now the next question is what is Q acting on the state? This question will answer both the question what states are Q closed as well as what states are Q exact. Because Q does not mix up oscillator number. Okay? So let's work that. Okay. So what was Q? I'm sorry, I know we're hitting the lunch boundary. 5 minutes, we'll do this. Q is equal to C m L minus m plus n minus n by 2 Cm Cn b minus m minus n minus c. Okay. Now let's act this Q we are resting on this motion. Okay. First, let's see what we get when acting with this alpha minus 1 mu. Okay? When we act on it with alpha minus 1 mu, you see, if you take some Lm with some large positive m, okay, it won't work because if you've got an alpha 1, you'll also have some other large positive alpha which will go and hit the vacuum and give you 0. Okay? So which state could possibly give you something non-zero acting on alpha minus 1 mu? Okay? Which state could possibly give you something non-zero acting on alpha minus 1 mu? If you think about it, you can say it's basically L1. Because L1 has a term, okay, that is alpha 0, alpha 1. Alpha 0 mu, alpha 1 mu. There is a term like that. This guy can contract away with this. And this guy needed to annihilate this vacuum. Because there's some momentum. Okay? If we had L2, the only time we would need an alpha 1 times alpha 1. One of the alpha 1s will contract with this, the other one will go and hit the vacuum and give you 0. Okay? If you had an L, anything small, let's say an L minus 1. Okay? The only way we could get an alpha actually, what am I? Yeah. Sorry. If we had an alpha L minus 1, then we would have had a C1. And C1 would go and hit the vacuum and give you 0. Okay? So anything with minuses won't work because the C will kill it. Anything with two high pluses won't work because the other guys will kill it. This is basically the only term that can contribute. Okay? So this term will give you alpha mu gamma mu. Alpha mu gamma mu, we probably got the number right. Because in L minus 1, in L1, each term occurs with a 1, right? There was a half, and then there were 2 terms. Okay? So acting with Q on this thing, one of the things that we do is alpha 0 mu, gamma mu. Alpha 0 mu is P mu after normalization. Some alpha prime stuff, which we work out. Okay, that's correct. What about the action of this guy? Well, this guy, what about the action on this guy? This on this will give you 0. Why is that? Well, this just passes through the C minus 1. Okay? This just passes through the C minus 1, and so the only term that gives you something non-zero is C0 L0. But C0 L0 exactly cancels what this C0 L0 gives you. So in the same way, this C0 passes through the C minus 1. Okay? So the combination of this and this acting on the state, this gives you 0. Right? Because this thing, this combination acting on the vacuum gave you 0, but this combination anti-commutes with C minus 1. So it continues to give you 0. Okay? So what's left is this guy. Okay. So what do we get with this guy? The only way we get something interesting is if we had a B1 here. Okay? Now, okay, so we've got a B1. So B1 can knock this guy out. B1 can knock this guy out, but we don't want anything negative here. So we've got B1. We could have, what could we have? We could have a C0 C minus 1. Or we could have, okay, wait. Okay, so we want to look at what we get with this stuff on this guy. We want to see when we get something non-zero. Now, anything that is positive goes through here, except B1. Right. So this guy is non-zero. Right? Because this guy gives us B1, C0, C minus 1. So we get a term here that is of the form B1, C0, C minus 1 acting on 0 times beta.
The B1 goes away.
What?
The B1 goes away.
Yes, B1 goes. Thank you. And we have to get the sign straight. But then we've got arbitrary coefficient. Anyway, we get the sign straight. Okay? Could we have got anything else? Suppose we took a B1 times C minus 2 C1. Then the C1 would go through and kill. That would work. Okay? Suppose we took B0. Okay, times whatever the B0 would go through and kill the state. So basically nothing else would work. Okay? So QBRST in this guy will give you a state, a term proportional to C0, C minus 1 and 0. Clear? Okay. Here we got alpha 0, and oh, by the way, here also we had a C0. This is because it came from C times T. Okay, so because L0 with a C0. And this C was left. Okay, and then there was the last state. That was the BI. This is B minus 1. Okay, so what do we get when we act with QBRST on it? Well, what can we get? Okay, so we could get something with a C1 here. Okay, so suppose we put a C1 here, we would get L minus 1. Okay, but the vacuum. Yeah. So what in L minus 1 could possibly contribute? So we have C1 and we have L minus 1. In L minus 1, the only term that could possibly contribute is alpha mu minus 1 alpha mu 0. Such a term could not exist. Okay? So this term would give us, acting on this, a term called alpha times C1 times alpha minus 1 mu alpha mu 0. Okay, what about from here? What can we get from here? Well, we want a C plus 1. Suppose we take C plus 1, C0, C B minus 1. That can contribute. Okay? So the C plus 1 will beat up the B minus 1, and you will be left with C0 times B minus 1. Okay? Alpha C0 B minus 1. Now we have to get the numbers right. Okay? So the action of QPRST, really sorry about this. The action of QPRST on this general level 1 state is what? Acting on, so Q acting on alpha B minus 1 plus beta C minus 1 plus gamma mu alpha minus 1. It gives you what? It gives you C0. Every state here has a C0. C0 here, C0 here, and C0 here. This also had a, no, this didn't have a C. This one, sorry, this didn't have a C0 because we chose C minus 1. Yeah, sorry. So it gives you C0 times beta B minus 1 of 0 plus alpha mu 0 gamma mu. Okay? Plus alpha B minus 1 on 0. Okay? Plus a state that is alpha mu minus 1, alpha mu 0 on 0. And this came with the coefficient alpha. Okay, we should go in just 1 minute, but let me just count host numbers. The state, suppose I assign host number 1 to C and minus 1 to B, and 0 to this. Q had host number 1 because it was C times T. So Acting on this, I should get a state of ghost number 1, so that's C0, that's good. Acting on this, I should get a state of ghost number 2, which is this, so that's good. And acting on this, I should get a state of ghost number 0, which is this and this, so that's good. Okay, so this is the action of Q, BRST of level 1 states. Okay, now what we want to do, is to check when are these states closed, and of the closed states, which are exact. I'm really sorry I messed up so badly in this class. So we have 3 minutes left for lunch, so we'll have to postpone this for the next class. I planned to talk about this and then to give you the general proof for the no-ghost theorem. I'll have to wait till next class. I'm sorry about this.
When is the next class?
Next class is not on Thursday, so I suppose Monday.